Hello, my name is Gareth Smith, and I'm the General Manager of Eggplant here at Keysight Technologies. And today I'm going to talk about bots that test, or retraining the Terminator. And this is really about the ability to auto-generate code on the fly for the purposes of continuous testing. The world used to be a simple place. The Mariner spacecraft had less than 100 lines of code in them. Even the Voyagers, our first interstellar spacecraft, and still going strong some 44 years later, had just a few thousand lines of code to run all their systems. Today, even the Pac-Man in your watch goes well beyond this number. Complexity can be pretty hidden, so take a basic Rubik's Cube, and the number you can see below it, I'm not going to read that out, is the number of unique combinations that a single cube can display. It means that if you spend a minute or two randomly turning different layers and levels within that cube, you'll end up with a combination that no one has ever seen before. Another, maybe less glamorous example is a simple and simplified workflow at a hospital. Here you can see there are 9 key stages in total, and each stage supports a different number of combinations, shown by the numbers below. So, for example, we have 21 different types of patients, and each patient can have 16 different types of medical history. So an obvious but limited set, but even in this simple flow, results in nearly 150 billion unique combinations. So the world is no longer a simple place. We can't possibly test all those different combinations with all this complexity, so we need a few tricks. Often things like out of scope help us narrow down or focus on what we think are the most important aspects, so we try ignore some of those real world factors, like changing a locale or system language while registering a patient. So we can at least start somewhere, but this is a little ad hoc and blinkered. There has to be a better approach. Science fiction is a good place to start looking. There are lots of real-world innovations that started in science fiction novels and movies that end up in reality. Lieutenant Uhura's earpiece in Star Trek is really an early Bluetooth headset. The modern defibrillator is a more controllable and slightly safer version than that of Dr. Frankenstein used. And then we have 3D printers or replicators, lab-grown meat, self-driving cars, and video calls, which have been much of the last 12 months for many of us. They're all concocted in the realm of science fiction before they change the world in practice. So where can we get some inspiration from for our problem? We need something that is able to sense the real, rich world, the environment as it is, make sense of it, interact with it, and understand it in all its rich billions and billions of different combinations. Well, there is one such system. Anyone with any technology background will have watched the Terminator series of movies and tried to feverishly read the overlaid text in the T-800's vision. In many examples of the first movie, we get to see an X-ray in how the mind of a Terminator works. It's analyzing the environment, understanding it, and interacting with it, normally shouting at things or stealing things. So the X-ray shows us two things if we look carefully. One, it does this by automatically generating code on the fly as it does this. Secondly, the source code it generates looks like it's 6502 assembler language, apparently from an Apple II. For the purposes of this talk, I'm going to focus on the first point and let the second one go as artistic license. So auto-generating code is a thing. There's a nice article in Wired called Now for AI's Latest Trick, Writing Computer Code. And that covers a number of aspects and technologies that are attempting to do this today. Foremost in the article is something called GPT-3 from OpenAI. GPT-3 is an enormous neural network trained on a huge amount of existing open source code. And it's capable of auto-generating code to create custom web apps, including buttons, text input fields, colors, by remixing snippets of code that had been fed. If we unpack this a little, the GPT-3 system has extracted a set of primitives, the language lexicon in this case, and has learnt the context, that is the real world use of these primitives and how they were used together. You can run your own mini Turing test by going to the doesnotexist.codes website and test your skill in identifying machine-generated versus human-generated code. So this is a click above the 6502 assembler instructions we saw on the T800 And now we're into a slightly more abstract set of commands, such as memory pointers, procedures, and so on. We can then obviously extend this level of abstraction to include richer constructs that can be stitched together on the fly. We can use more powerful keywords and even macros and use these holistically. What we are left with then is two things: a list of things or our elements that we can stitch together, and then an intelligent compiler that knows why, when, and how to stitch these elements together. So how would this intelligent compiler work in practice? All we've covered so far is the principle that the mechanism will generate the underlying code, but we need to ensure that the intelligent compiler is able to understand the environment it's in and what it can do about it and to it. There are three parts to this puzzle. The first is all about sensing the environment. We need to be able to understand and control whatever we're being asked to test. We can also think of this as our system under test. Self-driving cars use specific mechanisms such as video, radar, and LiDAR systems to understand their surroundings. Many software systems have APIs or human-readable screens. Whatever there are, the compiler will need to experience and affect the environment it's on. The second piece is a digital representation of that environment, some codification of what it's expected to interact with, and in our case, also test and validate. This is important because it becomes the point of reference for actions and reporting of any problems. Again, self-driving cars will use their systems to build out a synthetic 3D representation or model of the real world they're driving through, and they can use that to navigate. But here we'll use a more generic term for this model that we can borrow from the world of IoT or Internet of Things, and that's a digital twin. This is the digital equivalent to the real world environment. It's a proxy, but it gives us a way to express the world in a way that the technology can understand. And the third part is the intelligent core to glue everything together. It can understand the status of the real world from whatever sensors it gets access to. It can then map that to the digital twin so it can work out what the next best action to take is and what the intended outcome should be. Obviously, a key target for modern AI technologies. These techniques can interpret and comprehend complete and incomplete data sets and interpret vast quantities of this data from multiple different sources, all in real time, and crucially, learn from their experiences to optimize the future actions. So if we look inside this intelligent core a little more, in our world of quality, we can use the concept of automatically generating the most relevant source code at any one time to generate the most appropriate tests at any one time. We create a script, run that script, and then repeat that process. You can look at prior scripts, which is sometimes useful, but the goal is to just keep generating new ones while continually learning. In our world, things that we need to include are coverage. If it was our job as a manual human tester to ensure we have tested, in quotes, a new system, then we would need to ensure that we have tested as much of the different systems and interconnectivities between those systems as we possibly could. Here we're trying to intelligently recall which states and flows between those different states we have tried to result in a uniform but varied set of flows. We'd also want to exploit déjà vu. If I'd selected the state Arizona in my previous 3 tests for patient admissions and they all failed at that stage, then I'm going to use Arizona as the state for the discharge screen too, so I can see if it fails there. Here we're using our intelligence to spot the use of the state Arizona in the address fields, but that's just one factor. In reality, there are tens or hundreds of factors at the heart of underlying problems, and a human has no chance to easily correlate all these. In contrast, machines with AI algorithms were built for this level of pattern analysis and detection. The final thing we'd also want to include is noticing changes. If we spot something new, then let's start there before we go around to things that have not changed for some time. In practice, the AI used to intelligently auto-generate test cases for exploratory testing will use these strategies and others all combined into a single ensemble that will work together to select the next best action to take, or in our case, the next best thing to test. continually learning and updating its knowledge as each action is taken and the result verified or not. While this sounds less sophisticated than something as cool as a self-driving car, in reality, self-driving cars are presented with their intelligence, whereas in the world of testing, the environments and the systems vary continually and valuable patterns emerge and disappear. So it needs to continually learn as it goes along, like our Terminator friend. We have spent some time talking about the concept of automatically generating source code on the fly by intelligently stitching together existing elements and doing that based on feedback from any environment and referring to a digital twin as a reference. There's no way on a talk like this that I'm not going to end up by showing some of that in action. So what you can see here is a digital twin in the center. The blue boxes are used to represent the different screens on, in this case, a connected car app. The grey boxes inside the blue boxes are the actions that can be invoked. It's within these grey boxes that we define our elements, and whether these are keywords or small macros, our intelligent compiler will then carefully stitch together unique flows or tests here, continually validating the results of each action and learning from its experience to fine-tune the next test and then repeat this process. So now we have the automated technology that will automatically generate source code. We can use this to automatically generate test scripts for us. We can connect it to any system and get it to help improve the quality of that system or collection of systems. This can include standard applications, games, medical devices, websites, but we can also include robotics and electronic measurement systems to complete the full cyber physical range of testing. So for example, while our human-facing screen may appear to work okay, the radio frequency interference has exceeded some regulatory limits, or we find that a specific sequence of actions, again, all work correctly, but generate huge spike in battery use and would cause us big problems if we shipped. And I'm sure our friendly T800 would approve of that. So thank you for your time. I hope you enjoy the rest of the event.